Hello everyone, I am Dr. Sirajul Faizi. I welcome you in my YouTube channel. Today in this video, I am going to talk about pericyclic reactions. You can see this is a special pericyclic reactions. You know the reactions. Here is a special term pericyclic reactions. Now, I will show you the types of pericyclic reactions. The types of pericyclic reactions are distinguished by the number of sigma bonds made or broken. So look at here. Types of pericyclic reactions. Cycloadditions, sigmatropic rearrangements, electrocyclic reactions. Cycloadditions, you can see two new sigma bonds are formed. You can see here black one and black one. Two new sigma bonds are formed. And if it is reverse, then two sigma bond broken and then formations of this. So from here to here and here. So this is the plus or minus 2. Now sigmatropic rearrangement, one new sigma bond is formed. You can see this one is the sigma bond, but now it is broken. New sigma bond formed. Now here is the new sigma bond as another breaks. This one is break and new sigma bond formed. So del sigma is equal to 0. Now electrocyclic reactions. You can see here one new sigma bond formed without broken. You can see one sigma bond is new sigma bond formed. If it is break, then reverse reaction. So this one is plus minus 1. This one is plus minus 2 cycloaddition, and this one is sigmatropic. Now frontier molecular orbital. You can see HOMO of diene and LUMO of diene. So you have the psi 1, psi 2, psi 3, psi 4. So you can see this one is filled. All green are up. This one is psi. 2 green up, 2 green down. It is filled. So this one is filled and filled. So it is HOMO. And this is the diene. So psi 1 and psi 2 is the HOMO. Now you can see 2 terminal down and 2 center up. This is the LUMO and unfilled. Psi 4, you can see 1 up, 1 down, 1 up, 1 down. So that one is empty. So this is about your diene system. So you have the psi 1, psi 2 HOMO and psi 3 and psi 4 LUMO. Now you have here 2 electrons. Large energy gap versus overlapping. This energy gap, if it is large, then overlapping is difficult. A smaller energy gap, better overlap. So pi and pi star. This is the pi filled and pi star empty. Then you can see the HOMO of anhydride and LUMO of anhydride. Up, down, both are up. So now look at this picture. Diene and dienophile. HOMO, LUMO. Here HOMO, LUMO. So this energy gap and this energy gap is different. But HOMO of diene and LUMO of dienophile, this energy gap is small. So normal electron demand diene HOMO, and dienophile LUMO. Interactions are dominant. Now, friends, you can see new pi bond, new sigma bond, here, new sigma bond, new pi bond. This is the diene and this is dienophile. I will show you. This is the diene and this is the dienophile. So now you can see here new pi bond and new sigma. So this is the new sigma. Now you can see reactants, transition state, and product. So if you have the diene like this, if you have dienophile like this, so you will get these products. So this one is not observed, this one. So what happened? Bonding interaction in transition state between CO groups and back of the diene. So you have diene, this is the dienophile. So this is the situations. So new double bonds and CO groups end up at the same side of molecules. So this one is indo. You can see the product indo. You can see the indo additions, exo additions, and you can see the product. If you have the diene, you have the dienophile, you will get these two products. You can see the structure. This is your diene, this is your dienophile. So it gives this product. You have this is diene, you have the dienophile, it gives this product. You have the diene, you have dienophile. So it will give the two products, indo and exo. Exo 25 to 10% and indo is the meso product. So if you have this compound chiral dienophile and you have the chiral diene, you will get 1:1 mixtures of enantiomers. So now I will show you 4+2 cycloaddition. This one in the presence of heat is not possible. Why? Because you can see it is not matching. So LUMO of diene and HOMO of diene is not matching, Psi3, Psi2. So that's why it is not possible through the heat. Now dimerization occurs. You can see diene, here is dienophile, and presence of heat forming this cyclized product. So here is matching. So HOMO of diene and LUMO of diene is matching and forming. So count the number of electrons, pi electrons. The cycloaddition that do occur thermally, for example, the Diels-Zelter reaction have 4n+2 pi electron in their aromatic transition state. You know, my friend, the cycloaddition that do not occur thermally, for example, the dimerization of alkene and of dienes have 4n pi electrons in their anti-aromatic transition state. So you can see the cyclopentadiene exists as a dimer. Draw out the mechanism and explain stereochemistry. So you can see how this is the indo relationship between two alkenes. This is your diene, this is dienophile, then formations of this ring, and this is the integration. Now friends, if we now draw the frontier orbital in two components as they come together for the reaction, we can see first of all that the symmetry is correct for bond formation. Now we shall look at the same diagram again, but replace one orange dash line, the orbital that are overlapped to form a new sigma bond, so that we can see what is happening at the back of the diene. So you can see here matching formation of this product. So system react with back of that does not have non bonds. The bonding interaction in transition state between CO bond and back of diene. So you have the diene, you have the dienophile, you have diene, and then you can see new double bond and CO groups end up the same side of molecule. Now regioselectivity, you can see here diene dienophile forming these two products. 95% this compound, only 5% this compound. Diene dienophile gave this product. This one is 82%, this one is only 18%. So the questions of radioselectivity arises when both the diene and alkene are unsymmetrically substituted. Generally, there is a preference for the ortho and para orientation, respectively, as in example shown. You can see here. So you have substituted diene, dienophile. You will get the ortho is only products. Now you can see you have diene, dienophile. Para is the only product, 50%. This one is 94% product. That good and at low temperature. Very nice dish. So you can see the butadiene and acrolein. Butadiene is the here LUMO you can see, and LUMO of this acrolein you can see. So LUMO of unsaturated carbonyl compound, lower energy, unequal coefficients. Here you can see nucleophile from this side, green side, nucleophile from white side. So LUMO pi star of the simple alkene, high energy coefficient of the same size. Now, using experiment and theory, orbital coefficient are constructed. You can consider one substituted dienes, you can see the HOMO, LUMO, then substitutions. Now, energies, electron withdrawing groups, Z, you can see this. Carbonyl lower both the HOMO and LUMO, lower the both HOMO. Electron donating group, X, methoxyrize both the HOMO. Now you can see Dale's interrelations. Diene, dienophile will give this product. Appropriately paired orbital with two largest coefficient internal strong. You can see here diene, dienophile forming this product. This is the Psi2, this is the Psi2, HOMO of carbon dibutane, HOMO of butadiene. Now you can see the LUMO of unsaturated carbonyl compound. Here nucleophile is coming from the green side and this nucleophile from the white side. Low energy unequal coefficient. So orbital with two largest coefficient interact strongly. Now you can see the electron donating groups such as this is the Dimerization radiation. And what is the condition of Z? Z electron withdrawing or conjugated groups such as these groups CHO, C2R, COOH, CO2R, CN, NO2 halogen. It is so useful mnemonic. If you prefer a rule to remember, try this one. Pericylic reaction is cyclopentadiene with aromatic transition state. That is ortho and para direction. Now, Lewis and catalysis. Heat in toluene at 120 degrees Celsius sealed tube with tin chloride 5H2O at 0 degrees Celsius. You will get the two products. One is 93% resolved. Now, if you add more powerfully electron withdrawing groups, then this. So for anti-molecular orbitals, you can see Psi1, Psi2, Psi3, Psi4. You have this diene and diene. So what is Woodward-Hoffman rules? So I will discuss these Woodward-Hoffman rules in our next video. So if you like this video, then subscribe my channel and thanks for watching. And You can share it in your friend circle, in your relatives, so that every person will be benefited with this video. So thanks for watching.